Math 1314, Tyler Junior College, Section 2.5, Transformations of Functions. Graphs of Common Functions, Part 2. In the previous video, we categorized three specific functions: the constant function, whose graph is a horizontal line; the identity function, f of x equals x, whose graph is a perfect diagonal line; and the absolute value function, f of x equals the absolute value of x, whose graph was a v, whose corner was on the origin. In this video, we're going to look at three more functions, whose names are the squaring function, which is exactly what you think it is, the cubing function, and the reciprocal function. The squaring function is the function that squares its input, so it's just f of x equals x squared. We've talked about this one a little bit, so it shouldn't be a surprise about its graph. Its graph is a parabola that opens upwards and has its vertex at the origin. On a parabola, the vertex is the low point or the high point where the graph switches between increasing and decreasing. Its domain is all real numbers because this graph goes forever left and forever right. So negative infinity, comma infinity for its domain. However, its range is not all real numbers because the outputs are not every possible real number. You can tell because this graph does not go below 0. The lowest point on this graph has a y value of 0, so our range begins at 0 with a bracket, comma, the graph goes up forever, so its range goes to infinity. This graph is a combination of increasing and decreasing. Coming in from the left, the graph starts out decreasing on the interval that begins at negative infinity, and I say begins at negative infinity loosely, and ceases to decrease once it hits 0. That's where it turns around. At that point, the graph begins increasing on the interval that begins at 0 and continues to infinity. This graph has y-axis symmetry, which means that this function is an even function. So this is a graph that we've seen before, and we've analyzed quite a bit. It's not the end of our analysis of it. Wait till we begin chapter 3. If the squaring function is f of x equals x squared, what do you think the cubing function is? F of x equals x cubed. I do want to remind you that the name of a function is arbitrary. I could have called this g of x, or h of x, or w of x. Anything except x of x. So, what does the graph of the cubing function look like? Well, let's think about it. For positive numbers, when you cube it, it usually grows faster because you're multiplying 3 times in a row. I say usually because at the beginning of the graph, it's actually a little bit flatter before you hit the number 1. In fact, let me locate the point 1, comma 1 real quick, which is on not only that graph, but this graph as well. If you pick a number between 0 and 1 and multiply it 3 times in a row, you actually get a smaller value because you're multiplying by a number less than 1. So between 0 and 1, it's a little bit flatter than the parabola, just a little. It's hard to draw perfectly. But then it totally flips the script. Once the x gets bigger than 1, multiplying 3 of them instead of 2 of them produces a much larger output much faster. For example, if we squared the number 2, we get 4, but if we cube it, we get 8. If we square the number 3, we get 9, and if we cube that, we get 27. So once you cross the number 1, it actually accelerates its speed quite a bit. Now, it's not vertical, it's just steeper. But what happens on the left side? Same thing? Sort of. On the left side, the x's are negative, and when you raise a negative to the third power, it stays negative. In general, when you raise a negative to an odd power, it stays negative. So I get the same kind of flatter at the beginning, steeper after the number 1 effect, except on the negative side of things. So it's kind of flat, hits the point -1, comma -1, and at that point it starts to accelerate. This graph, appropriately enough, is called a cubic. It doesn't have a cute name like parabola, it's just called a cubic, which sounds more like an adjective than a noun. So, what's the domain? Well, just like a parabola, this goes left and right forever. You may not get that impression, but it does go forever in both directions. It's just ridiculously steep. So it has the illusion that it's just going vertical, but it's not. Plus, think about it. I can put any number I want in here. There are no restrictions to the domain. I can let x equal anything. But what about the range? Is it the same as the parabola? Well, since range is y values, and this graph goes down forever, this range begins at negative infinity, and it goes up forever. So the range is all real numbers as well. How about increasing, decreasing? And remember, when you're looking at that, you're thinking from left to right. From left to right, this graph is always increasing. So this graph is increasing on its domain, which is negative infinity to infinity. Even function? No. If I fold the right half across, it doesn't land on the left half. Odd function? Yes. If I rotate the right half 180 degrees, it lands on the left half. So this is an odd function. In general, anytime you have x to an even power, you get what looks like a parabola, but the bigger the power, the flatter it is in the middle and the steeper it is on the ends. If your function is f of x equals x to an odd power, you'll get a graph like this, but the larger the power, the flatter it is in the middle and the steeper it is on the ends. Reciprocal function. Well, to reciprocate, a fraction means to turn it upside down. So if we take a function that says f of x equals, we want to reciprocate that, we need to think of this in the form of a fraction. And you can turn anything into a fraction by putting it over 1. So if I have x over 1 and reciprocate it, I get 1 over x. Now, this graph is a little unique from the other ones I'm going to show you in this section. Let's start with its domain. I know that's a weird place to start. Can I put any number I want into this function? Almost. I can put every number in there except a single value. What one value will make this fraction undefined if I try to put that value into the denominator? Answer, 0. The domain of this function does start at negative infinity, but it has to stop at 0 in parentheses to exclude the 0 because you can't reciprocate 0. You can't divide by 0. But that's only the numbers on the left side of 0. The domain also includes the numbers on the right side of 0. So parentheses 0, comma, infinity, close parentheses. Since the domain is consisting of two separate intervals, we need to join them with the union symbol. We'll discuss the range in a minute, but let's get the graph first. First off, if I reciprocate 1, I get the number 1. So I know my graph will go through that point. But what happens as we go further out to the right? As the x starts getting larger, we start getting smaller and smaller fractions. So as we go out towards the right, this graph starts getting closer and closer to the x-axis. Now, will it ever touch the x-axis? Well, no. To touch the x-axis means the output would equal 0, and the only way a fraction can equal 0 is if its numerator is 0. This one never will be. So this graph gets closer and closer to the x-axis, but it never actually touches it. Now what happens is we go to the left of 1, and remember, we can't cross 0. As we go to the left of 1, we can start putting in fractions like 1/2, 1/3, 1/4, 1/5. And as we reciprocate them, we get numbers like 2, 3, 4, and 5. So we get the reverse action here. We start skyrocketing, but we can't put in 0. So just like the graph was approaching the x-axis over here, it's also going to approach the y-axis over here and never touch it. Now, is that the entire graph? No. That's just the graph for the positive inputs. For the negative inputs, we get the same thing, except when you reciprocate a negative number, it's still negative. So the other half of the graph is the same boomerang-looking shape that's getting progressively closer to both the x and the y-axis without touching them. Later on, we'll discuss that phenomenon when we discuss asymptotes. But the graph of the reciprocal function is unlike the graphs of the other functions we're looking at in the sense that it's disconnected into two branches, a branch down here in quadrant 3, and a branch up here in quadrant 1. Now that we have the graph, what's the range? You would think it's negative infinity to infinity, but there's one y value excluded, and that's y equals 0. So the range is actually the same as the domain. You can get out any number except 0, and you can put in any number except 0. Is this graph decreasing or increasing? Well, we have to look at both branches. On the left branch, as we move left to right, we are decreasing. What we're also decreasing as we move left to right on the right branch. So it's decreasing on both halves of its domain. It's decreasing on negative infinity to 0 and 0 to infinity. Is it an even function? No. If I fold the right half across the x-axis, it will not land on the left half. Is it an odd function? Yes. If I take this branch in quadrant 1 and rotate it around 180 degrees, it would land on the other branch. This is an odd function. When we get to the end of chapter 3, we'll be talking about this type of function a lot more.